Welcome to homework.
Okay, so this is problem 24.17. In this problem, we have a normal interference experiment, but actually for this one, we have inserted a piece of plastic, okay, in front of the lower slit, okay. So, and we are asking what should be the thickness, the smallest possible thickness of that piece of plastic that will produce an interference pattern where instead of having a maxima at the center here, we're actually having a minima. So the configuration is something like this. Okay, and if you go back to problem 24.13, where we have proven that in order to get a minimum at the center position, actually the central the two beams here should have a wave, a phase, they should be out of phase by 180 degrees, okay? So, and this corresponds to a difference in wavelengths, which is lambda over 2. In order to describe this graphically, I can say that if we call the beam coming through the first slit to be 1, and the beam coming through the second slit to be 2, okay? So the first beam will be something like this, okay, and the second beam will be something like this. So they are completely out of phase, and they will add destructively. So they will add to 0 at the central position here, okay. And this difference is like half a wave, half a complete wave, which corresponds to a difference, which is lambda over 2. Okay, so we want the distances, the difference between the distance covered by this beam, beam 1, and the distance covered by the second beam, beam 2, to be delta D, to be lambda over 2. Now, if we want to get delta D, okay, we have two beams. So for the beam going through the piece of plastic, we have actually the velocity inside the medium is equal to the distance traveled in the medium, which I labeled here by L, over time. Okay, so we can get the time Bt is equal to L over C medium. And now there is a very important fact that we have to consider here, which is actually the wavelength of the light beam will change inside the medium. Okay, so lambda medium is equal to lambda over n, and hence C medium will be lambda medium, which is just lambda over n times f. But we know that lambda f is the normal C in air or vacuum, so it's C over n, right? And hence we can get T to be L over C over n, which is just n L over C. Now, this was T for the second beam, okay, 2. Now for the first beam, I want to know what would be the distance covered by the second beam during the same time interval. So during the same T2, what will be L prime? And the velocity in this case is just the velocity of light, the speed of light in air or vacuum, which is just C. So, and T is equal to T. So I can equate this one with this one, right? And get N L prime over C is equal to, no, sorry, N L is equal to L prime over C, cancel the C's, and so N L is equal to L prime. Now, we know that we have proven that delta D should be lambda over 2, and actually delta D is just the difference between the distances covered by the two beams, which is L prime minus L. And from here, we know that L prime is just NL, right? We can go back here, substitute for L prime to be NL minus L. So N minus 1 times L, where I had got L out of here as a common factor, is equal to lambda over 2. And then we can solve for L, okay? So L will be just lambda over 2 times, oh, sorry. L is lambda over 2 times n minus 1. Lambda is 680 times 10 power minus 9 over 2 times 1.6 minus 1, which will give us 567 times 10 power minus 9 meters. And this should be the thickness of the plastic plate in order to get the interference pattern where the minimum is actually located at the center of the screen.